So today's topic is continuing the idea of probability mass functions, but now we're going to kind of combine that with conditional probability. So today's topic is basically conditional probability mass functions. And this is not really any new material in some sense because we already kind of have all the pieces for this, right? So we talked about conditional probability a couple weeks ago, and we talked about probability mass functions like last week. So this is just kind of combining the two things, okay? So let's remember what we called a probability mass function. So remember the definition of a probability mass function, right? It's basically the probability that x takes on a certain value. Or if I wanted to be really kind of, over the top, I could go back to my original experiment and say, okay, it's the probability that, of the outcomes in my sample space, which ones had the random variable mapping that outcome to this numerical value, right? So again, if we wanted to be really, say, okay, well, the experiment is, say, flipping a coin and recording the heads and tails pattern, and the random variable is counting the number of heads in that pattern to give me a number, okay? Or to kind of think about, saying, okay, I've got the sample space for my original random variable, or my original experiment, and then I've got a whole bunch of, sections of the sample space, partition of the sample space, where these pieces of the sample space, for example, maybe this is the one that maps to the random variable x equals k. So it's kind of like saying I'm just kind of looking at the total probability of all the stuff that maps to k, okay? And so now what I want to do is I want to combine this concept of a PMF with the concept of conditional probability, okay? So I want to be able to talk today about the probability that the random variable takes on some value given some condition, right? Which is a different way of saying the probability that I get this value k given this other event. So for example, I could ask, what's the probability that it takes me 5 seconds from now to get a communication packet given that I've already waited 5 seconds, right? So there's some event and I'm conditioning that event to find out what are my probabilities, right? And so that concept hopefully is just going to be following on from what we already know, right? So let me write down what I just said. E.g., the probability that a packet takes 5 more seconds to arrive, given that we already waited 5 seconds. Or we already waited 10 seconds, doesn't really matter. Right? So the idea of conditional probability, if you remember before, was saying, okay, I've got my sample space, I've got my partition of the sample space, right? These are all the different kind of values that the random variable can take on, and then this is my condition, C, and it's kind of like saying, okay, now I tell you that you're inside this ellipse C, now what's the probability of each of the random variables, right? So observing that this event C happened will change my balance of how high these arrows in the PMF are, okay? Now we have to have, the probability of C has to be greater than 0 for this to make any sense, right? I mean, the condition has to actually be a possible thing, okay? So let me just kind of be explicit about what this means, right? So this is like saying the probability that I get a given value given this condition is the probability that I get this and that this condition is true over the probability that condition is true, which is kind of like saying, it's the probability of kind of like this, well, okay, I think this is a good place to stop, right? Basically, this is the normal thing, you know, this and this over the probability of that, right? So it's kind of like normalizing by the amount of probability that's in the condition, and I rebalance the probabilities, okay? So let me just do a couple examples of this to make this clear. So let's suppose that I'm flipping a coin, and I'm flipping that coin that maybe is not fair, okay? Maybe it's a biased coin. So I've got a biased coin, and I do 5 independent flips. And then I could ask something like, you know, what's the probability that I got 5 heads given that the first 2 flips were heads? Okay, so I can ask that question. So it's kind of like saying, okay, you know, suppose that my x is the number of heads. That's my random variable. So it's kind of like saying, you know, what's the probability that I got this pattern given that I know the pattern is head, head, and then some other stuff, right? That I got the first 2 flips were heads. Well, let's just write out my definition using this conditional probability formula. So it's like saying I got this and this over the probability that I got this by itself. Okay? Well, one way to think about this is saying, okay, well, if the probability of success is P, then the probability that I got 5 heads on the top is P to the 5th, right? And, you know, this and this is basically the same as this by itself, right? I can't get this without having that. The probability on the bottom is the probability that I got just 2 successes, and I don't know what happens next. So it's like saying I got 2 successes. So the probability that I got this given that is p cubed. So if I use, you know, so say I have a fair coin, that means p equals a half. So that's like saying the probability of having 5 heads in a row with this fair coin is 1 over 32, pretty unlikely, but the probability that I get 5 heads in a row given that I already saw 2 heads would be p cubed, which is an eighth, which is a lot bigger than 132, right? So knowing that this event happened, knowing that I got 2 heads already, makes the probability of getting 5 heads in a row much more likely, right? And so if I were to, so this is still just a number, right? This is still just a probability, but if I want to make this into a probability mass function, I could say something like, you know, if x is the number of heads, I could ask, what is the PMF of x given that the first 2 heads were, or the first 2 flips were heads, okay? So let me make a whole PMF out of it, right? So I could say the probability of x, or maybe I can use k here. So the probability, let me write this again here. Given that I have 2 flips already, well, what would it be? Well, again, if I go back to my kind of original fair coin, let me just kind of draw this over here. So the before situation was saying that a different way of saying this is like the probability of x given that x is at least 2, right? It took me at least 2 flips already. So that's like saying the old distribution here was a distribution of x before, right? It was unlikely to get 0, a little bit more likely to get 1, a lot more likely to get 2. And if I compute these probabilities, this is the 1/32 that I got before. And if I compute the numbers, it turns out that these numbers are 5/32, and these numbers are 10/32. So this is kind of like the before PMF, right? Now I tell you the condition, and I want to know what is the after PMF, right? So I tell you that I already got 2 heads, right? So I know now that if I think about what the PMF looks like now based on this condition, the condition shifts the probability, right? So now there's no possibility of getting 0 because I already know I got 2. There's no possibility of getting 1, right? There is some possibility that I only stick with 2, and then there's some possibility of getting 3 heads, 4 heads, 5 heads, right? So I can figure out, okay, so it's kind of like saying I've already laid down that these 2 things are heads, and now I'm asking, well, what's the probability that of the remaining flips I got 0 heads, 1 head, 2 heads, 3 heads, right? And I know that, you know, this is probability an eighth, this is probability an eighth. There are 3 ways this can happen and 3 ways that this can happen. So my kind of rebalanced probability is like this. So this is basically the probability of the number of heads in 5 tries, given that I already had 2 heads. So it's kind of like the after or the conditional PMF. So we haven't really learned anything new here, right? It's just saying that, you know, if I tell you some condition, that changes the probabilities, right? That moves the probabilities around, okay? So this still has to satisfy all the same rules as a normal PMF, right? I have to have positive probabilities. These numbers have to add up to 1. You know, it's just like a new PMF, right? A before PMF and an after PMF. Okay, so let me stop and ask. Any questions or comments? Let me do a bunch more examples to make this concept more concrete, okay? So let's suppose I'm, you know, waiting for a bus. And the number of minutes we must wait is uniform on, you know, the possibilities 1 minute, 2 minutes, up to 20 minutes, okay? So that means that the probability distribution is 1/20th for each of these possibilities and 0 otherwise. We know that has to be true because I need all the probability to add up to 1, right? And now I could ask, what's the probability of getting a certain value given that I told you it was at least 8 minutes that we waited, okay? Again, I kind of write this out. You also may sometimes see this in this kind of notation, where you see the conditional in the bottom. This is kind of like a slightly different way of you know, different notation for the same idea. And again, I just follow my nose on the definition. It's the probability that x equals k and x is greater than 8 over the probability that x is greater than 8. Okay. So first, what is the probability that x is greater than 8? Well, since everything is uniform, that's like saying, I know I'm not in 1, 2, 3, 4, 5, 6, 7, 8. I must be in 9, 10, 11, and so on, right? So that probability is 12 over 20. What's the probability that x equals k and x is greater than 8? Well, that's like saying, okay, let's look at the PMF. The PMF is just originally uniform, right, on these numbers. And each of these values is 1/20th, right? So it's like saying, okay, well, this is equal to, if I'm somewhere here, say like 14, right? I'm greater than 8. Here's my dividing line. I guess since I said greater than 8, my dividing line is kind of like here, right? So if k is greater than 8, this is like saying, well, the probability of, say, x equals 14 is 1/20th for those values that are greater than 8. And if I ask about like k equals 3, well, x equals 3 and x is greater than or equal to 8, I can't have that, right? That's 0. So if I put it all together, this thing here, if I move on to this page, is equal to 1/20th over 12/20ths equals 1/12th if k is greater than or equal to, or if k is in the range 9, 10, 11, to 20, and it's 0 otherwise. All this means is that this was my before PMF. Now I tell you, okay, you were greater than 8, then all the probability mass kind of shifts around to the new condition, right? So the new PMF, the conditional PMF, looks like a uniform distribution on just the values that are left. And the height of these arrows is 1/12th, and these numbers now all become impossible. Right? So it's just kind of like, you know, I had a before PMF satisfied the rules, I have an after PMF satisfies the rules. Okay? Comments, questions? Yes?
P of x equals k and x is greater than 8 is the 1/20, is that the answer to that?
Right, well, it's 1/20. So for example, let me be explicit. So suppose I have like a specific value, like P of x equals 14 and x equals 8, right? So this is the same thing as this in this case, right? Because this and clause, you know, I'm already greater than 8, so I don't learn anything from this, right? So this is just 1/20th by itself, right?
Oh, so you just take the lower one.
I just take the more restrictive one in this case, right? Okay, let me do something in a slightly different way, okay? So kind of the reason that we talk about conditional probability is because in electrical engineering, you often get some sort of setup where you've got, okay, I tell you what the PMF of a given random variable is under certain conditions, right? Here is the amount of time it takes to produce this widget if the machine is working well, and here's the probability if the machine is broken, right? So usually you're given information in the form of conditional probabilities, conditional PMFs, right? So we learned in a way already about this total probability theorem, right? This says that if there are, say, m kind of possible states of nature, if this is a partition of the original sample space, so if one of these things has to happen, then the overall PMF of a random variable is like the probability of x given b1 times the probability of b1 plus the probability distribution of x given b2 times the probability of b2 plus dot, dot, dot. So basically I look at all the conditional PMFs and kind of weight those by the probability of each of those things happening, right? This is just in a different way writing it like this. I look at all the conditional PMFs and weight them by the probability. So to make this a little bit more concrete, let's suppose that we only have two possibilities. So here's an example, like a medical kind of example, okay? So let's suppose that I let x equal the number of additional years a randomly chosen 70-year-old will live. Okay? And now I'm going to tell you, playing the role of these BIs is going to be conditions like medical conditions, okay? So let's suppose I have H is high blood pressure. And N is normal blood pressure. Which is like not H. So basically, everyone has either got high or normal blood pressure, okay? And so then I tell you these conditional PMFs. I say, okay, the PMF of X given high blood pressure, I'm going to tell you is a geometric random variable with P equals 0.1. And the conditional PMF with normal blood pressure is going to be a geometric random variable with P equals 0.05. Okay? So let's remember what that means, right? So for example, that means that the conditional PMF given high blood pressure is going to be this 1 minus P to the K minus 1 times P. We already know that. So in this case, the P is 0.1. So it's like saying that this is my PMF for a high blood pressure person, and then this is my PMF for a normal blood pressure person. Okay. And now I can say something like, okay, if 40% of the population, if 40% of 70-year-olds have high blood pressure, what is the PMF of X overall, right? So over the whole population, if I pick someone random, how many more years do I expect them to live, right? So it's kind of like saying, well, that's going to be a weighted combination of these two PMFs that I'm given, right? And so if I apply this total probability theorem from before, this is like a situation like this where I only have two possibilities, two, B sets. Either I am high blood pressure or not high blood pressure, right? And all I need to do is add those two PMFs up, weighted by how likely that is in the overall population. So in this case, it's just going to be the overall distribution is the PMF given I'm in the high state plus the PMF that I'm in the normal state, weighted by the two categories. And if I want to be really explicit about it, I just multiply these things together. That's like saying, here's the high blood pressure PMF times the probability of that happening, which is 0.4, plus here is the normal blood pressure PMF times the probability of that happening, which is 0.6. It's basically just like the weighted sum of the two original PMFs. Okay? And if I wanted to draw it, I'm not going to draw it, but if I wanted to draw it, I would have basically, it would look like, one geometric random variable PMF looks like this, and another one looks, a little bit different with different height arrows, and I multiply this by 0.4, and I multiply this by 0.6, right? Now, kind of the reason that we set this up sometimes is that now I might want to ask, okay, so if I pick a random 70-year-old, what is the expected number of years, right? So that requires me to kind of combine two expected values, right? So we learned last time that once we know the p-value for this geometric random variable, we can look it up in the table and say, oh, I remember now that the mean is the 1 over p, right? So let me just kind of say that from last time, the expected value of a geometric random variable was 1 over p. And so what does that mean for this example? That means that the expected value of x given that I'm in the high blood pressure case is 1 over 0.1, which is 10. And the expected value of x given that I'm in the normal case is 1 over 0.05, 0.05, which is 20, right? And this is kind of why maybe this model makes sense, because you're going to live a little bit longer if you don't have high blood pressure, right? And the nice thing is that what I would like is that if I want to ask about the expected value of somebody random that I pick from the population, that hopefully it's kind of like the natural combination of these two PMFs, or these two expected values, right? Because if I gave you this thing over here and asked you to compute the expected value using the direct formula that we talked about last time, you could imagine that it would be a huge pain to do, right? Very tedious to figure out how to even approach that, right? Whereas, luckily, by the total probability theorem, the same one we used to build the PMF, let's kind of back up and think about, okay, so let's rederive what does it mean, expected value. So the expected value of x is the sum over the possible values of the random variable times the probability of getting that value. And now I could say, okay, well, I could break this thing up here as the sum of the states of nature that I might possibly have, right? These are like the conditional PMFs, weighted by how likely that is to happen. And now I'm going to switch these two sums around. Kind of put parentheses around here like this. This now is basically what we would define as the conditional expected value, right? This is like saying, what would the expected value be if I was in state BI? And so if I apply that to this example, this is just like saying that the expected lifetime of a given 70-year-old is just the conditional expected value times the probability that they're in that situation plus this conditional expected value, right? So I can very quickly find the expected value saying, okay, well, it's 10 times the probability that I'm in that state plus 20 times I'm in the probability this state, right? So it's going to be 4 plus 12 is 16. So luckily, that lets me go from an extremely tedious computation to a very quick computation, right? If I kind of know what are the conditional expected values, I can get the expected value for the whole random variable. So questions about this example? Okay, let me do another example. So I actually don't really have that much to say today other than doing a bunch of examples that are all illustrating the same idea, okay? So let me give you a more electrical engineering kind of example. So let's suppose that, you know, yep, question? This one here? This guy? Okay, I'll leave this guy up here. Okay, so I'll leave that up while I'm setting up the next example. So the next example is saying, okay, let's suppose that I'm transmitting web pages. And I think about kind of, again, I could make this more complicated, but let's suppose that I have kind of two states of nature, right? Either the web page is all text, like, you know, Wikipedia, more or less, or it has got text and images, right? So I know that web pages with images probably take longer to transmit, longer to download. They require more packets to use, right? So let's let X be the number of packets that I need to transmit a web page. And let's suppose that I have two possibilities. Either the page has images. I guess that these days every page has images, but what are you going to say? Or the page has no images. Just like text. Okay? And I'm going to give you some conditional PMFs, right? I'm going to say, okay, the probability of the number of packets given that it is an image page, that number could be anywhere between 1 and 50. So I'm going to give it a uniform distribution on 1 packet up to 50 packets. And if I'm a text web page, I'm going to say it's a uniform distribution on up to 5 packets, right? So a text page will definitely take, on the average, a lot less to transmit than a image page. And I'm going to suppose, maybe not that realistically, that the probability that I have an image page is a quarter, right? So maybe this was from the days when I was in college, when we didn't have all these images on our web pages, right? So again, this is a good exercise, just like the last problem. This is a good exercise in just kind of like, you know, if I tell you, okay, it's a binomial, or it's a uniform, or it's geometric, you should kind of start to know what that means in terms of the underlying PMF, right? So let's be a little more explicit about what the conditional PMFs are. So the PMF in the image case is going to be equal to basically 1/50th for values 1 through 50 and 0 otherwise. And the PMF for a text page is going to have possible values 1 through 5 with probability 1/5. And so now I can ask, okay, what's the overall PMF? What is the probability distribution on the number of packets? Well, it's going to be 1/4 times the conditional PMF given that I'm in the image case, plus 3/4 times the conditional PMF that I'm in the text case. And so what would that be? Well, I know it's going to be a number between 0 and 50, right? So when I'm in, so certainly for k greater than 50, I have no probability of that happening, right? For k between 1 and 5, there are basically two ways that can happen. You know, either I'm an image page, which is probability 1/4, and then I have the PMF is 1/50, 1/50, or I'm a text page, and the probability of that, or the PMF there is 1/5. Right, so this is going to be like, do some quick side math, 1/200 plus 3/20 is the same as 31/200. Right, so this number here is 31/200. And then in the case of up to 50 packets, between 6 and 50, the only way that can happen is if I'm in the image case, right? Not possible for the other guys. So the probability of that happening is, again, just 1/200. And so this completes the whole PMF, right? And I can make sure that I'm, you know, kind of a sanity check. The values there should all add up to 1, right? So let's just double check. So I have 31/200. I have 5 of those possibilities. And then I have 1/200. I have 15 of those possibilities. So I have 155. Wait a second. No, I have 45 of these, that's why I have them. So I have 155 plus 45/200 equals 1, right? So I'm pretty happy with that because I ended up getting what I thought. And so if I think about what the PMF looks like if I were to draw it, it looks like, you know, I've got a lot of probability on values 1 through 5. Each of these arrows has height 31/200. And then I have much lower probability on the values 6 through 50. Each one of those has probability 1/200. And then I got nothing beyond that, right? So this would be my overall PMF. And so just as an aside, so if I ask you on a homework or on an exam to give me, you know, a sketch and a formula, this is kind of what I mean, right? So here, this is an explicit formula that tells me, if I tell you k, what is the actual number, and this is a sketch that shows me you understand how to interpret that as a picture, okay? So let me pause and ask, any questions or comments about this? So now if I bring it to I didn't do anything really conditional yet. Now I could say, okay, what's the probability distribution of x? Yeah, I could ask, what's the probability distribution of x given that I tell you that I'm less than 10, okay? So I have some number between 1 and 10. What's the probability of each of those numbers, right? So first I have to, you know, compute. Well, let's just use the definition. This is like saying the probability of x equals k and x is less than or equal to 10, given the probability that x is less than or equal to 10. I have to compute first the denominator, right? So the denominator is, I have basically adding up the first 10 values here. So I have 5 times these tall sticks, and I have 5 times these short sticks, and that's going to be 155 plus 5 is 160 over 200, which I guess I can simplify as 4/5. So that's like saying that if I were to take the first 10 values here, that up to this point, there's 4/5 of the total probability, right, if I added all that stuff up. And now the conditional PMF is just like a rebalancing of that series of sticks by the total amount of probability there, right? So all I'm going to do is I'm going to take these numbers here, and I'm going to divide them by this number, right? So that means that the PMF, given that I'm in the less than 10 category, well, so certainly if I tell you I'm less than 10, then for any value greater than 10, I have 0 probability. For these first 5 sticks, k equals 1, 2, 3, 4, 5, I have 31 over 200 was the original value divided by 4/5, which is going to be 31 over 160. And then for these next 5 values, I have 1 over 200 divided by 4/5, which is 1 over 160. And so the result is something that looks kind of the same, except the values of the sticks are different. So now these values become 31 over 160, and these values become 1 over 160. And then nothing happens beyond 10. Questions about this? So now I could ask, okay, what's the expected value of this conditional distribution, right? So given that I told you you're in the range 1 through 10, what's the expected value? Well, I would just go ahead and compute it, right? So the expected value of x given x is less than or equal to 10, well, it's going to be basically the sum over the possible values of the corresponding PDF values. So it's like saying I have 1 times the probability of getting 1 is 31 over 160, plus 2 times the probability of getting 2 is also 31 over 160. So I have 5 of those probabilities, and then I have 6 times the probability of getting 6 is 1 over 160, and 7 times the probability of getting 7, and so on. So in this case, that's like saying I would have 15 times 31 over 160 plus 6 plus 7 plus 8 plus 9 plus 10, whatever that is, it's going to be 16. 16 is 32 plus 8 is 40. And so I'm going to get whatever that number turns out to be, 505 over 160. Right? So I mean, we're just using the same definition of expected value here, just on this new PMF. So even though there's a lot of notation that maybe is a little bit new and confusing, the concept is not really any more complicated than thinking about, okay, I'm going to multiply each of these possibilities on the x-axis with the probability of getting that possibility on the y-axis, right? And I add those numbers up. That's what the expected value is, okay? Questions on this example? Now suppose I wanted to compute the variance, okay? So we talked about variance last time also. So what would the conditional variance be? We could talk about that also. Right? For example, the variance of x given that x is less than or equal to 10. Well, again, same idea, right? The definition of variance is it's the expected value of x squared minus the expected value of x squared, right? We already computed this from over here. This we already know to be whatever this number is. What would be the expected value of x squared given this? Well, it would be the probability of getting 1 squared times that probability, plus the probability of getting 2 squared times that probability, plus the probability of getting 5 squared times that probability, plus 6 squared times that probability, and so on. And I'm not going to work all this stuff out, right? But I could compute whatever this number is and plug it into here and subtract this, and that would be my conditional variance, right? So one thing that we talked about last time was that it's not true. So one thing that I saw coming up on homework 6, and I'm going to talk about this on Thursday, is that, you know, while it is true that the expected value of some linear function of random variable, we kind of explained why that was this, right? It is not true that the variance of this thing is equal to this. Okay, that was kind of a thing that you maybe got tripped up on homework 6. We'll talk about that on Thursday. Kind of one reason immediately that you can see why this is not true is that, you know, suppose I just had variance of x plus b by itself, right? That's like saying I have a PMF here with some variance, and then I just take the same values and I shift them by b, right? So if things start at 0 over here and they start at b over here, I mean, I can kind of see that while I've changed the mean, I haven't changed the variance, right? I've got basically the same shape of distribution I had before, and the spread of values around the mean has to be the same, right? So adding a constant to a random variable doesn't change anything, right? What the actual answer is, right? So the variance of ax plus b is just going to be a squared times the variance of x. If you think about, you know, you've got a factor of a in here that you can pull out of this expected value. So let me just kind of say, remember that, you know, variance, you know, I'm not sure what I want to say about that. I guess I went off on a digression. That, you know, basically, you know, variance acts differently, right? So to apply it to our example, you know, in the same way, the variance of x you can't get by combining the two variances. It might be tempting to think that this is true, but it's not. Like in our blood pressure example. Usually for variances, you actually have to work out the value, you know, the expected value of something squared, right? Okay. Question? the variance of a times x is a squared times the variance of x, right? Let's just do that. Let's think about why that is, right? So the variance of ax, this is like saying the expected value of ax squared minus the expected value of ax squared, right? So here, this is like saying I have the expected value of a squared x squared minus, I know that I can pull out the expected value here, squared. I can pull the expected value out of here like this, the a. And then I can see this is just like this. Right? So I guess I could have done that last lecture, but this is a good place to do it now. Other comments? So let me do a couple more examples. So I'm not sure why I have this in my notes here, but I guess I might as well do it because it's right here. So let's think about the Poisson random variable. Just to kind of get us, again, let's suppose that I have x equals the number of packets that arrive at my router in a 10 millisecond interval. And I model this as a Poisson random variable with a mean of 2. Oh, I know I have this here. Well, let's just do it. So what would be the probability of, what would be the PDF of x given that x is greater than or equal to 2? Okay. Well, I know that so again, kind of what this Poisson PMF looks like is probably something that kind of peaks at 2 and then tails down, right? And so first I would have to compute what's the probability that I'm in this area here, right? Well, the probability that I'm greater than or equal to 2, the easiest way I think about it is as 1 minus the probability that I got exactly 0 packets minus the probability that I got exactly 1 packet, right? Which would be 1 minus the probability of getting 0, so I have to remember what is my Poisson PMF. It's going to be 2 to the k over k factorial e to the minus 2, e to the minus alpha, right? So the probability I get 0 is 2 to the 0 over 0, so I just get e to the minus 2. And the probability I get 1, if I plug 1 into that equation, I get 2 e to the minus 2. So it's 1 minus 3 e to the minus 2. So that's the denominator of what I need. And then the probability then here is going to be, well, it's going to be 0 if k equals 0 or 1, because I already told you that it's not one of these values. And now if I told you it's not one of these things, I just have to rebalance these arrows by this factor. Right? This is the amount of probability that's left, right? So it's going to be 2 to the k over k factorial e to the minus 2 divided by this amount. Which is, some mess, but basically it's a rebalanced version, right? So the reason now the reason I put this in my notes. So I want to tell you about one particular property of the geometric random variable, okay? So remember, the geometric random variable is the one that I get by saying, okay, so how many flips will it take me to get ahead, okay? Now, well, let me just start writing and then I'll give you some intuition. So the final thing I want to say for today is what's called the memoryless property of the geometric random variable, right? So let's say that x is a geometric random variable with probability of success p. Okay, that means that this is my PMF, right? I have 1 minus p to the k minus 1 failures followed by a success. And now I want to know, what is the probability that x is greater than some number of flips, given that I told you it's already greater than this number, okay? So for example, what's the probability that x is greater than 10, given that x is greater than 6, okay? Well, I can compute what is the probability that x is greater than some value, right? It's the, or greater than k0. Like, it's the sum from k equals k0 plus 1 to infinity of this PMF. And you already have done this computation probably about 5 times so far, right? So this is a different way of saying I can just kind of say something like this. So I've got this thing times p. This infinite sum I know is 1 over 1 minus p. This is the same as 1 over p. So this p and this 1 over p cancel out, and we get this. I feel like we already did this on one of the homeworks, right? So how much probability is there in the tail of the geometric distribution? It's this number, okay? And so now I could say, okay, well, I can look at this conditional probability and say the probability that x is greater than this number, given that I'm already greater than that number, is going to be 1 minus p to the k plus k0 over 1 minus p to the k, which is these 1 minus p's are going to cancel out, and I'm going to get 1 minus p to the k0, which is the same thing I would have gotten if I asked for the probability that I was greater than k0 in the first place. So what does this mean? Why am I so interested in this? Well, what this means, for example, is it's like saying the probability that x is greater than 10, given that x is greater than 6, is equal to, if I write this in a different way, the probability that x is greater than 6 plus 4, given that x is greater than 6. And what I just proved is that this is equal to the probability that x is greater than 4. So why is that interesting? It's interesting because this is like saying that if I have a coin flip, that the coin doesn't remember what happened, right? It's like saying that, you know, if I want to know what's the probability that it takes me 10 flips given that 6 have already occurred, it's the same as the probability it's going to take me 4 remaining flips, right? The coin doesn't remember the bad flips. It just kind of knows, okay, you know, if we fail in one trial, then going forward, conditioned on that, is the same as just starting over, right? I know I've already lost 1 flip, and I just add 1 to my number of trials. So let me try and write that down in some useful way. So the interpretation of this is that the coin doesn't kind of remember previous failures. That is, if the success hasn't already occurred, in some number of trials, in the first K trials, then the probability of needing K0 more trials to get the success is the same as the probability of needing K0 trials in the first place. Kind of a different way of looking at this geometrically, or in a sketch form, is saying that if I look at the geometric PMF and I have these are my decaying values, and then I say, okay, you know, I haven't succeeded so far, what's the probability here? If I were to basically renormalize these arrows, I would still have a geometric distribution. Right? And that's kind of interesting because it doesn't usually happen, right? This is the only case where that kind of thing happens. Like if I look back at the example I did with the Poisson random variable, right? So if I revisit, just draw it here, it's not true for this Poisson example. So if I have something where the Poisson PMF kind of grew to a point and then decayed off, and then I said, okay, if I were to cut off this distribution and renormalize this part here is no longer Poisson. This is some other, you know, just like arbitrary conditional PMF, right? So this is only true, only works for the geometric random variable. Doesn't work for any other kind of random variable. Right? You can imagine the same thing is true for like binomial, right? So if I were to, you know, take a binomial and throw away the left pieces and renormalize, that thing doesn't look like a binomial anymore, right? The geometric one is the only one that has this property, and it happens to be true because each one of these sticks is, you know, 1 minus p times the other one, because they all have the kind of same ratio. That's why it turns out to be true.